Okay, today we're going to start off by looking at number 6.5, or question 15 from section 6.5 in your homework last night, which was on page 417. Number 15 says, for what numbers between negative 2 pi and 2 pi does the graph of tan x have vertical asymptotes? So for all of the values of x between negative 2 pi and 2 pi, does tan have vertical asymptote? So tangent has a vertical asymptote when what is true? Whoops. All right, so tan x is equal to sine x over cosine x. So tan x is going to have vertical asymptotes right when cosine x equals 0. And so if we're thinking about the unit circle, right, cosine x is going to equal 0 when the x-coordinate on the unit circle is equal to 0, which happens at this point and at this point, right? So at 90 degrees and then 270, right? And so between, so 9 degrees and so pi over 2 and 3 pi over 2, between 0 and 2 pi are the two ones, and then it's also going to occur at negative 90 and negative 3 pi over 2. So the answer will be negative 3 pi over 2, negative pi over 2, positive pi over 2, and 3 pi over 2. Right? So just like with a rational function, when the denominator of our fraction equals 0, that's where our vertical asymptotes lie when we're dealing with trigonometric functions like this. Other questions?
No, that's about it.
All right. So today we're going to start off by talking about, we've already talked about tangent and cotangent. Today we're going to talk about secant and cosecant. So, for instance, let's just start with cosecant. We know that, so graph of cosecant and secant. Right, so cosecant is just equal to 1 over sine x. So we can sort of make a chart to figure out what cosecant is going to be equal to. Here's my values for x. We'll just go between 0 and pi over 2 as we did yesterday. So we'll do 0, pi over 6, pi over 4, pi over 3, and then pi over 2. Oops. All right, and then we'll look at sine and then cosecant. So we know that sine of 0, once again looking at our unit circle, sine of 0, sine is the y-coordinate on the unit circle, is going to be 0, right? So then cosecant is 1 over 0, which means it's undefined at 0. So just as before, we're assuming that that's probably going to result in a vertical asymptote at x equals 0. Sine of pi over 6, hopefully at this point we're starting to get these ones down. Sine of pi over 6, we know that that's the smaller angle, so it's going to have the shorter side opposite, which is the side that corresponds to y. The smaller number of the two is 1/2, yes. And so the reciprocal of that is 2. Pi over 4 is square root of 2 over 2, and the reciprocal of that is 2 over the square root of 2, which when you rationalize it ends up becoming just square root of 2. Pi over 3 is square root of 3 over 2, which when you rationalize it becomes 2 over square root of 3, right, which will then become 2 square root of 3 over 6. Sorry, let me. So it ends up being 2 over square root of 3, which if we rationalize the denominator is 2 square root of 3 over 3. And then for pi over 2, it's 1. And so cosecant is also 1 at that point. All right, and then at that point, let's think about what's going to happen. Well, we've gotten to pi over 2, so we've gone all the way along here. And now, that's the largest that sine x gets, and so sine x starts getting smaller, and so cosecant then is going to start getting larger because we're dividing by a smaller number, a number that's less than 1. Until, bam, eventually we get back to y being 0 at pi, and there we'd expect to have another vertical asymptote right there. And then, of course, after that we'll be in the negatives, come up to -1, and then back down to, back down to negative infinity, and then skip across to positive infinity again, and then come back down to 1. All right, so what that means for the graph, I guess I'll try and draw it in right here. Right, if we graph this, let's just do it between, I'll do between 0 to 2 pi, so 1, 2, 3, 4. So pi over 2, pi, 3 pi over 2, 2 pi. And so what happens then is we start at undefined, so we have a vertical asymptote along the x-axis here, and the function and then the function's going to end up coming down to 1, right? It's going to come down here, it's getting smaller and smaller until it sort of stops there and then goes back up, and then we have a horizontal asymptote right here. Right, and then on the other side here, it'll come up to -1 and then go back up. Right. So that's what it looks like. And interestingly, its relationship to sine, and knowing these points right here, the point where it has this relative minimum and the point here where it has this relative maximum is really important. In addition to knowing where the vertical asymptotes lie. And notice it never gets to 0, so there are no x-intercepts for cosecant. And what's interesting about this is if we were to draw the graph of sine, right, on the same graph, it would look like this, right? And I drew it sort of poorly there. But you can see that they intersect at this point and at this point right here. At pi over 2 they intersect because they're both 1, and at 3 pi over 2 they're also both 1. And so you can almost just graph secant by putting these little parabolas here, if you want to think of them as that, on top and on bottom of sine here, right? Because they sort of fit right on top and then right on bottom of the bottom part there. So that's what the graph of cosecant looks like, and secant's going to be very similar. For the graph of secant, we know is just 1 over cosine. Right, and so if I go ahead and make a table of values here, just like I did before, x, cosine, and then secant, do 0, pi over 6, pi over 4, pi over 3, and pi over 2. Right, cosine is 0. We're looking at the x-coordinate now of the unit circle is 1. Cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 3 is 1/2. And cosine of pi over 2 is 0. So for secant, that means it starts at 1, and then it goes to 2 square root of 3 over 3, and then square root of 2, and then 2. It's just getting larger, right, as we go along here. And then eventually it's undefined. Right, it's undefined at pi over 2 because it's 1 over 0 now. And so what that means for the graph of secant you have pi over 2, pi, 3 pi over 2, and 2 pi. So once again, I'll mark off 1 and -1. This one actually starts at 1 and then starts climbing, getting larger and larger and larger until we have a vertical asymptote at pi over 2 like we saw. So it's sort of going to look like this. Whoops. Right, and then It's going to come from down here, hit -1, come back up there, and then it will go down here and then hit -1 again. So once again, just like with secant, it sort of mirrors, in a way, cosine, because cosine looks like this, right? They intersect right there, and they come back up, and they intersect right there again. So once again, you can just put the secant curves right on top and right on bottom of the cosine curves if you know what cosine looks like. Okay, so that's secant and cosecant. So let's look at some examples of graphing those. So if I gave you a function y equals 2 cosecant x -1. Go ahead and take a shot at graphing that one right there. Also, please graph one full cycle. I'm going to graph one full cycle of 2 cosecant x -1. So multiplying it by 2 is going to increase well, we don't call it amplitude in this case, just because, like, just with the cotangent and tangent, we don't necessarily have an amplitude, but it is going to increase where cosecant comes down to. So it used to come down and come up to 1 and -1, right? Now that's going to happen to 2 and -2, right? So if it wasn't for this -1 here, it would come down to 2, and then go up to -2, and down to 2, and so forth. But because of this -1, we have to push everything down by 1. So instead of going up to 2 or going down to 2, it's going to go down to 1, right, and go down to -3, right? And then still going to have it set. We haven't changed the period at all or anything like that. So we have pi over 2, pi, 3 pi over 2, and 2 pi here. And so what we want to do here is identify where the asymptotes are going to be at just regular cosecant, which has asymptotes at 0 and pi and all multiples of pi, because it's 1 over sine, and sine is 0 at multiples of pi. All right, and then it's going to come down to 1, so it's going to pass through the point pi over 2, 1. It's going to pass through the point 3 pi over 2, -3, right? And so it's sort of going to look like this. And once again, it's really important to identify those relative max and min. So identifying what point that is and what point that is important, knowing where it is. Okay, so all we did was increase, we did a vertical stretch by 2 and shifted it down by 1 here. Pretty straightforward. Now, what I forgot to mention through really quickly, secant x and then cosecant x, right? First of all, there's no amplitude, unlike sine and cosine. Only sine and cosine have amplitude. Or at least we don't call it the amplitude in the case of secant and cosecant. And so there's no amplitude, but it does have a period because it is a periodic function, even though it's not what we would call a sinusoidal function. The period in this case is the same as the period of its function that it's a reciprocal of. Secant's a reciprocal of cosine. Cosine has a period of 2 pi, and so secant has a period of 2 pi. And it has asymptotes, vertical asymptotes, at, for secant, they occur when cosine is equal to 0, so at pi over 2, 3 pi over 2, 5 pi over 2, etc., right? And it also would go for negative pi over 2, negative 3 pi over 2, etc. So all odd multiples of pi over 2 is where it has asymptotes. For cosecant x, once again, no amplitude. Has a period of 2 pi as well, because it is the reciprocal of sine, and sine has a period of 2 pi. We saw that in the graph. And it has asymptotes located at 0, pi, 2 pi, and all multiples of pi, also negative pi, negative 2 pi, and so forth. And neither of these have any x-intercepts, right? For either of them, no x-intercepts. So yeah, there's no zeros. Okay, so that's all we're going to say about secant and cosecant for today. We're going to get on to talking about phase shifts of sinusoidal functions here. So, phase shift is the last piece of the puzzle for us. Phase shift is a fancy way when we're talking about periodic functions and we do a horizontal translation of some sort. In the case of a periodic function, like sine and cosine, we call that a phase shift. All right, and so if I have some function, y is equal to a sine of, and we're just going to keep calling the multiplier on x as omega, minus, and we're going to start using the Greek letter phi, or phi. Right, and this is going to end up resulting in some sort of a horizontal shift, though. But if we remember back to what we talked about translations of functions earlier, if we're going to combine a period change like w, or like omega here, with some sort of shift, we have to do it in a specific order, right? Because if we go ahead and we change the period of the function and then we shift it by this much, that's going to end up affecting it in a different way. Because once the periods change, this is going to result right here in a much larger shift than we had initially intended. So to actually, we want to shift it essentially before we do our change in period, right? And so normally the way we would like to write our periodic functions is to factor out the omega, right? And if we do that, we get phi over omega here. And a lot of your book sort of does it in a weird way by having a phi here be the variable, as opposed to just having this be the variable initially. A lot of other books might just say an alternate way of writing it would be y is equal to a sine of omega times x minus whatever the phase shift is going to be, which we could just call that c, I guess, for now, as opposed to having this be a weird fraction because you factored out the omega value there. In any case, though, this is going to the omega tells us what our new period is going to be, and the c will tell us the exact amount of the phase shift, or the exact amount of the horizontal shift. How much am I pushing it left or right? And then we're going to go ahead and change. And because of the order of operations here, we're going to do this operation first, and then we'll go ahead and change the period. But the thing is, once again, if we change the period first and then move it left or right, it's going to have a much larger or smaller effect than what we would intend. So we always want to have this factored out, whatever the period is there. Okay, and so this ends up being our phase shift, right? And then oftentimes we also have a vertical shift as well, right? We'll push it up or down by some amount, and we'll just call that d for now. Right. And so we have our phase shift, we have our vertical shift. Omega results from whatever our period is, so omega is just going to be equal to 2 pi divided by the period, right? And our amplitude, just as before, is just equal to the absolute value of a. Right. So we have our vertical shift, our phase shift, our omega, which results in our new period, and then our amplitude comes from the value, the absolute value of a. Okay, and so let's go ahead and look at that in an example here. So we have the function y is equal to 3 sine of 2x minus pi, for instance. 3 times sine of 2x minus pi. First of all, let's go ahead and identify all the different properties of the function. So first of all, what is our amplitude? So my amplitude is 3. What's the period? If we know what omega is, how do I find my period?
It's 2 by 2. So
Yeah, it's the original period divided by whatever the multiplier is, right?
Okay, so it's pi.
Which is pi, yeah. Now, the phase shift, we have to do a little factoring, right? To be able to figure out what the horizontal shift is, we have to rewrite this as 3 sine of 2. And if we factor out the 2, we end up with x minus what?
X minus.
What happens if I factor out the 2? I end up with x minus... What would I have to multiply 2 by to get negative pi if I distribute it back through? What times 2 is equal to pi? Pi over 2?
Oh, yeah.
So essentially, whatever you factor out, right, just ends up in the denominator of what's left over. And then if you can simplify it, that's good. So that means our phase shift, the amount that it's getting pushed left or right, is pi over 2. And what direction? Pi over 2 to the right, because it's always the opposite direction that we think of it when it's on the inside of the function. Pi over 2 to the right, or a positive pi over 2 phase shift, whichever way you want to think of it. All right. So the next step is to go ahead and actually graph it. Okay. So let's go ahead and do that. So the amplitude is 3, so it's going to have a and then the amplitude's 3, and there's no vertical shift, right? So it'll have a maximum of 3 and a minimum of negative 3, right? The period is going to be pi, so it's going to have a full cycle of pi. Now, if the phase shift is to the right by negative pi over 2, where should we start our cycle if we're shifting it to the right by pi over 2?
At pi over 2.
Yeah, let's get it started at pi over 2. Yeah. And so if it starts at pi over 2 and it has a period of pi, it'll have completed a full cycle by when? By when?
Oh, pi.
What's pi over 2 plus pi?
2 pi over 2. Yeah, okay.
It's going to be 3 pi over 2, yeah. So it's going to do a full cycle between pi over 2 and 3 pi over 2 because of the new period. So it's going to do that. So that means we'll have this is going to be 3 pi over 4, right? And this will be 5 pi over 4. And so because it's signed, does it start at its maximum or does it start at 0?
Say again?
Does sine start at its maximum or 0? So when we start at pi over 2.
0.
Start at 0, go up to its maximum for 3 pi over 4, then go down to 0, hit its minimum at 5 pi over 4, and then get back to 0 at 3 pi over 2, right? So that's how we're going to graph this with the phase shift and everything. And of course, so what I like to do is start wherever the phase shift pushes it over to, right? And graph one full cycle from there, and then just fill in the rest of the graph based on that. So then, of course, if we have pi over, whoops, let's do this in red. If we have pi over 4 right here, and 7 pi over 4, we'll end up looking like this, hitting our maximum, and then going back down, and then hitting maximum up here, and then going back down. All right, so it's been pushed over by a full pi over 2, and its period's been reduced. So we do the phase shift because of the order of operations that's going on here, we do the phase shift first, and then we do the change in period afterwards, which is why I start at wherever the phase shift pushes me to, and then I, of course, change the period after that, right? So it's shifted over by pi over 2, and it has a new period of pi, right? So that is why we have to factor out, because if we didn't, like if we look at this right here, right, if we forgot to factor out the 2, we would think that the phase shift was negative, was pushed right by pi, right, and the period is 2. And so the way we would have to graph this is we would have to change the period first, right, and then shift it to the right by pi, right? And so if we did that, we would end up with it starting right here, wouldn't we? Which would be it's a way bigger shift than what we would indicate there. So if we want an actual phase shift of pi over 2, then we need to have it sort of done out like this. Okay, and because and the whole reason is what's going to happen here is if you, let me go back actually, I'm like rambling. So for this next one, I'd like you to go ahead and graph y is equal to 2 cosine of 4x plus 3 pi plus 1. Okay, so we have every single, so this is the first time we've had every single type of function transformation going on. We have a vertical stretch, horizontal stretch, we have a horizontal translation, also known as phase shift, and we also have a vertical translation. So go ahead and give that one a shot, and be careful with this vertical translation where the maximum minimums go in terms of how high and low they are. When we're graphing this, the first thing we want to do, just like we did before, is to go ahead and factor out the coefficient on x, leaving us with x plus what?
3 pi over 4.
X plus 3 pi over 4, yeah. All right, and then, of course, we have the plus 1 there. Let's go ahead and identify all the different things. My amplitude, of course, is 2. My period is going to be 2 pi over 4, which is going to be pi over 2, right? And the phase shift is 3 pi over 4. And then we also have a vertical shift of 1. So before we start graphing here, one thing that's important to notice is because we have plus 3 pi over 4, this phase shift right here is going to be a phase shift to the left, right, by 3 pi over 4 instead of to the right. So that means that we're going to be starting on the left side of the x-axis when we draw one cycle. So we have to keep that in mind when we're going ahead to draw our coordinate grid here. So we should make sure that we include a little piece to the left of the x-axis, sorry, the y-axis as well. And so the first things first, let's deal with the amplitude and the vertical shift to figure out where our maxes and mins are going to be. So my amplitude is 2, and I'm doing a vertical shift of 1, meaning that my new maximum, if there was no vertical shift, my max would be 2, my min would be negative 2. But if I move everything up by 1, my max becomes 1, 2, 3, and my min becomes negative 1. And anytime I do a vertical shift, I should always draw my midpoint line, which in this case is going to be positive 1, right? That's where we're going to essentially treat that like our new x-axis when we're graphing our sine function here, or sorry, cosine function. And so let's go ahead, and our phase shift is to the left by 3 pi over 4, and our period is pi over 2. So what I'm going to do here is I'm going to draw, here's pi over 2, here's negative pi over 2 and negative pi. And I'm also going to need, since our phase shift is by negative 3 over 4, I'm going to need negative 3/4 pi and negative pi over 4 as well. Right, and then on the other side here, I'm going to draw, pi over 2, 2 pi, 3 pi over 2, and 2 pi. All right, so if I go ahead here, I'm going to start at negative 3 pi over 4 because it was a phase shift left by 3 pi over 4, and then I'm going to complete a full cycle in pi over 2. So if we take negative 3 pi over 4 and we add pi over 2 to it, where do we end up at the end of our cycle? At negative pi over 4, right? Negative 3 pi over 4 plus pi over 2 brings us all the way to negative pi over 4. Right, we're also going to need the eighths here, so that would be negative 3/8 and negative 5/8. I'm not going to write those in because I don't have enough room, but that's negative 3/8 and that's negative 5/8 pi. Okay, so let's go ahead and start drawing this. So it's cosine. Our function is cosine, so that means we're starting at our maximum value and then going down from there. So our starting point should be 3, our maximum, at our phase shift starting point, which is negative 3 pi over 4. Then we'll get down to our midline value by negative 5 pi over 8, and down to our minimum value at negative pi over 2. Then back up to our midline value at negative 3 pi over 8, and then back up to our maximum at pi over 4. So it should look something like that. If it was, so that's one full cycle. And then we're just going to sort of fill that in. We'll fill that in all the way to 2 pi, let's say. So that means I got to get all my pi over 4s in here. Know your pi over 4s, folks. Know your pi over 4s. This is where knowing your fractions comes in really helpful. And we also need, and I'm going to put dashes in between these to represent all the multiples of pi over 8, because they are going to be important for graphing this as well. All right, and so I'm just going to go ahead here, and I have to hit my midline there, my minimum down here, right, negative 1, and then my midline again right here, and then my maximum, midline, minimum, midline, maximum, midline, minimum, midline, maximum, midline, minimum, midline, maximum, midline, and my maximum is getting a little bit too small here, and minimum. All right, so my amplitude sort of trailed off here. These should all, of course, be a little bit taller, but I think you get the general gist of how we're going to go ahead and treat this and graph these. So once again, the process is first start off with your amplitude and your vertical shift to figure out where your maximum and minimum value should be and where your midline should be. Always draw your midline if there is a vertical shift. Then start, once you figured out what your phase shift is, start by shifting the whole thing over by that amount and then start your cycle at that value that you shifted over to. And then do one full cycle and then fill in the rest over however long, for however many cycles or for how long of a domain over which you are asked to graph it. All right, so the next topic here is fitting sinusoidal functions to data. And so sinusoidal functions are so important because they are periodic, and meaning they repeat themselves, over and over again. And there are many things in real life that act just like that. One example is the average temperature, the average monthly temperature in a specific part of the world, right? It's pretty constant, right? And it repeats itself over and over again. Another example might be the tides here in Portland, for instance, or anywhere. Tides have this sort of sinusoidal behavior where they go up and down and up and down. Waves are sort of like that as well. And so we can use sinusoidal functions, cosine and sine functions, to model all sorts of natural phenomena or even man-made phenomena that which makes them very, very useful in that regard. So what we're going to do here is we're going to take this table of average monthly temperatures here for some location. I'm not really sure where it's supposed to be. Probably probably somewhere in the Northeast, though, if we have an average temperature of 29.7 in January. In any case, though, we're going to use this table of data to build a sine function that models the average temperature for any given month. So if we plug in a month, it will give us the temperature. And so they've actually nicely already for us numbered the months, because of course we can't use, the only way we can model this with a sine function is if we have numerical data. So each month has been already given a number, which makes sense anyways, 1, 2, 3, 4, 5. The same numbers that the months always get, of course. And so that's going to be that's a table of our x values, and these are the table of our y values. So before we even make the function, let's go ahead here and let's identify all the different various properties. So first of all, what is the maximum value? What's the maximum temperature that we have here? I believe it's July, right? Where it's 73.5 degrees. My minimum temperature is in January, right? Which is strange because usually February is colder, but whatever. In January, it's 29.7 degrees, right? And so that's my maximum value, and that's my minimum value, right? And so what I need to do here is from the maximum and minimum value, I can tell what the amplitude of this oscillation is, right? And I need to know the midline value, because the midline value will tell me what the vertical shift is, because clearly we can see that the midline right here is not the x-axis, right? It's been pushed up. There's been a vertical translation, right, by about that much there. So we need to figure out where is that midline, because that's going to be our vertical translation. And what is our amplitude? Our amplitude is going to be what? Half the distance between the max and the min, right? So let's go ahead and figure that out. So my amplitude is just half the distance between the max and the min, which is going to be 73.5 minus 29.7 over 2, right? And if we go ahead and plug it into our calculator, we end up getting 58.65, so that's my amplitude. So that's going to be my A value. So that's the amplitude of the temperature oscillation. And my midline, right, well, how do we figure that out? If we know this is halfway above it and halfway below it, we know the max and the min. How do we figure out the midline value? Isn't the midline value just the average of the maximum and the minimum? Yeah. So to find it's just, instead of 73.5 minus 29.7, it's just 73.5 plus 29.7 over 2. And that midline will be our vertical translation. Well, first off, I made a mistake on the amplitude here. The amplitude should actually be, as some of you probably have noticed, the amplitude should actually be 21.9. Plug that one into the calculator wrong. And for the midline, we'll get, and then our midline should be 51.6. So I've identified, and so that's going to be my vertical. That's my vertical translation. And the amplitude is my A value, of course. So I found 2 of the 4 pieces that I need for my sinusoidal function. Now I have to go ahead and figure out what my period is going to be. How often does this repeat? Well, if we look at the data here, right, it repeats every how many months? How many months are in a year?
12.
12. So we want our period to be 12. So my period is 12, and so that means my omega value is just going to be 2 pi divided by 12, and so it's going to be pi over 6. Right, so my omega value has to be pi over 6. Now the last piece of information I need to know is what is my, how can I model this with data? And here the answer to this question is that there's actually more than one way to do this, right? But what I would do is I would say I would look at the graph here and figure out, and the question is where do the maximums and minimums occur, right? Well, my minimum value actually occurs at 1, right, which is just to the right. So my minimum value occurs at 1. My maximum value occurs at 7. All right, and so what I can do here is probably the easiest way to do this is you can either use cosine or sine. It doesn't matter which, right? Because You know, and so the answer to this question is there's more than one way to answer this question. But what I would do is I would figure out, okay, where's my maximum? And cosine starts at its maximum value, right? So what should my phase shift be to have a cosine function that starts at 7?
You can ask the right or just the actual number.
Well, because if I don't do a phase shift, my cosine is going to start its maximum value at 0, right? But I want the maximum to actually occur at 7. So what should I do? Shouldn't I just shift it to the left by 7? Or sorry, to the right by 7? Yeah. So my phase shift should be, what should I put in for a phase shift?
7.
Yeah, phase shift is just going to be 7 in this case.
I was thinking too hard.
Okay. And so, unfortunately, I didn't leave myself enough room to actually write the function, so we'll do it in the next page. So that will do it for today. Your homework is on the next page here. So this is your homework for today. So the 6.5 stuff, this 6.5 homework, the 6.5 homework is off the old handout that I gave you yesterday. And the 6.6 homework is going to be off the new handout that I will email out to you today. So, everyone have a great weekend, and we'll come back on Monday. One thing I forgot to mention on yesterday's lesson that I did mention to everyone in class today is that there will be no class from next week from Wednesday through Friday, which is July 23rd, I believe. To the 25th. Right, so that's next week because I'm going to be away for those 3 days. So we will adjourn on. We'll come back on Monday, but we're only going to be in class on Monday and Tuesday of next week. All right, have a great weekend, everyone.